Welcome to today's tutorial on SQL window functions. Today we will learn how to write powerful SQL queries that ranks data, calculate running totals, and perform advanced analytics, all without complex subqueries, joins or aggregations. By the end, you'll master the most powerful and widely used window functions with clear, real-world examples. Let's get started.
Here's what we'll cover in this session on SQL window functions. We'll begin with the basics. What are window functions, how they work, and how they're different from traditional group by, which collapses rows, unlike window functions that retain row-level detail. Next, we'll explore key functions like row number, rank, dense rank, sum, max, min, lead, and lag, explaining when and why each one is used. We'll bring this to life with real-time use cases using employee and sales tables, common datasets for reporting and analytics. For every use case, we'll look at the SQL query, review the result set, and provide a quick interpretation of the output. By the end, you'll understand not just the syntax, but also how to apply these functions effectively. Before we dive into writing queries, let's first understand what window functions are. These are also known as analytical functions or OLAP functions, and they're designed to calculate values across a set of rows that are related to the current row and return value for each record. What makes them special is that they let you perform aggregations, like sums, averages, ranks, without collapsing the rows. This means you can get insights like running totals or employee ranks, while still seeing all the original details. Think of it as group by summarizes, window function enhances. To better understand this, let's compare a basic group by with a window function.
Let's start by reviewing this sample employees table. It has 8 rows, each representing an individual employee. Every row includes the following fields: ID, name, department, salary, and hire date. The employees are distributed across 3 departments: sales, IT, and HR. Now, say the business wants to know the total salary cost per department. To do that, we use a basic group by query on the department column. This query groups all employee records based on their department and calculates the sum of salaries in each group. Behind the scenes, Oracle does the following: finds all employees in each department, aggregates their salary values. However, there is a key limitation with the group by clause. We are only allowed to include columns used in the group by and aggregated expressions like sum, salary. That means we cannot include columns like name, hire date, or even employee ID unless they're part of the group. As shown here, the result only contains 3 rows, 1 for each department. The problem? We lose all row-level detail. We don't know which employees made up these totals, or when they were hired. This makes group by useful for summary reporting but not ideal when you want both summary and detailed data together. And that's where window functions shine. They allow us to compute totals, ranks, comparisons, and trends, while preserving all original rows. So in checkmark summary, use group by when you only care about aggregated results. Let's start with a common SQL challenge. Imagine you're asked to create a report showing each employee's salary alongside their department's total salary. Your first instinct might be to use group by with some function. But here's the problem: group by collapses your data. You lose all individual employee details and only get department summaries. To solve this, we typically write queries using aggregate functions combined with joins, subqueries, or common table expressions. But in all these cases, we end up repeating the same aggregation logic, which makes the code harder to read, and also less efficient, especially as the data grows. This is exactly why window functions were introduced. They solve the core limitation of group by letting us calculate aggregates while still keeping all row-level details, in a single, elegant, and performant query.
Let's look at the structure of a typical window function in SQL. The syntax consists of 4 key components: the window function itself, the over clause, an optional partition by, and an optional order by. Now let's walk through each of these components. Window function. This is the analytical function you want to apply, like sum, rank, row_number, or lag. Unlike regular aggregate functions, these don't remove rows, they calculate values relative to the current row. Over clause. The over keyword is what turns a normal function into a window function. It defines which rows the function should consider as its window, a sort of moving frame of data. Partition by, optional, partition by breaks the data into logical groups, similar to how group by works, but it doesn't collapse rows. The window function restarts its calculation for each partition. Order by, optional but important for ranking. Order by inside the window tells SQL how to sort rows within each partition. This is crucial for functions like rank and row_number, where order impacts the result. Summary. Together, these components let us analyze rows in context, produce aggregates, assign ranks, or look at neighboring rows, all while keeping every row in the result.
Remember our previous slide where we used group by to get department totals? And to include employee names and salary columns, we used complex joins and subqueries to combine result. Now let's see how window functions solve this elegantly. We have a simple select with all employee columns, plus a window function. The key part is sum, salary, over, partition by department. This calculates the total salary for each department, but here's the magic, it doesn't collapse our rows. How it works. The window function works in 3 steps. Step 1. Partition by department groups our 8 employees into 3 departments, sales, IT and HR. Step 2. For each partition, sum, salary, calculates the total. Sales gets 16,500, IT gets 21,500, HR gets 9,500. Step 3. Every row in each partition gets the same total value attached to it. Looking at our result, Alice, Bob, Charlie, all sales employees get 16,500 as their department total. David, Eve, Frank, all IT employees get 21,500 as their department total. Grace, Henry, both HR employees get 9,500 as their department total. Notice we still have all 8 original rows with their individual details intact, but now each row also knows its department's total salary. Key insight is, this is the power of window functions. They give you both individual detail and group level insights in a single query, without losing any data.
Let's explore dense_rank, a ranking function that requires the order by clause and handles ties differently than regular rank. Query breakdown. Our query uses dense_rank, over, partition by department order by salary descending. Notice dense_rank takes no arguments, it's just parentheses. The order by clause is mandatory because ranking needs a sort order. How dense_rank works. Dense_rank partitions employees by department, then ranks them by salary from highest to lowest. The key difference. When salaries are tied, dense_rank gives the same rank but doesn't skip the next number. As of now we do not have any employees within a department who has same salary, hence no tie. We will see tie example in upcoming slides. Looking at our results. Sales department, Bob ranks first with 6,000, Charlie ranks second with 5,500, Alice ranks third with 5,000. IT department, Frank ranks first with 8,000, David ranks second with 7,000, Eve ranks third with 6,500. HR department, Henry ranks first with 5,000, Grace ranks second with 4,500.
Let's see how rank and dense_rank handle ties differently using our modified data where Bob and Charlie both earn same salary 6,000 in sales department. Our query uses both rank and dense_rank, with identical over clauses. Both require order by and take no arguments, just empty parentheses. When Bob and Charlie tie at 6,000 salary, both get rank 1 in rank and dense_rank function, whereas next person Alice, rank function gives him 3 and skips 2 unlike dense_rank gives him 2 with no gap, hence it called dense rank. Let's analyze the result in detail. IT and HR departments have no ties, so both functions produce identical results. In sales, Bob and Charlie both rank 1. Alice gets rank 3 with rank function but rank 2 with dense_rank function, so the key difference is rank skips numbers after ties, dense_rank keeps consecutive numbering. You have to choose based on your business logic and needs which function to use.
Lead and lag are powerful analytic functions that let you access the next or previous row's value, great for analyzing trends over time, like monthly sales. Lag function looks backward, whereas lead looks forward. Both functions typically take 2 arguments, the column to read and an offset, like lagged, sales underscore amount, 1, for the previous month, or led, sales underscore amount, 1, for the next month. By default, if no row exists at the offset, they return null unless a default value is specified. In this case, we don't use partition by because the data is all from 2024. But if you need to analyze by city or product, you can partition accordingly. This gives you current, previous, and next month's sales, all in one view, helping you calculate trends and changes efficiently. Let's walk through the results set. In the first row, previous month sales returns null, because there's no previous month. But lead gives the next month's sales, helping us look ahead. In the middle rows, lag and lead both return values, allowing direct comparison with the previous and next month. In the last row, lead returns null, since there's no future row. This pattern clearly shows how lag looks backward and lead looks forward in the results set.
Let's start with row number, one of the most fundamental window functions. Looking at our query, we're using row number with partition by department and order by salary descending. This creates separate numbering sequences for each department, rank by salary. Now, here's where row number gets interesting with ties. Notice Bob and Charlie both earned $6,000 in sales. You might expect them to get the same rank, but row number doesn't work that way. Row number assigns unique consecutive numbers regardless of ties. So Bob gets rank 1, Charlie gets rank 2, even though they have identical salaries. The assignment is arbitrary. It depends on how the database physically stores the rows. Hence, row number is perfect when you need exactly one record per rank, like pagination or creating unique identifiers or ranking duplicate records. Let's see how max and min work as window functions. This query gives us each employee's salary, along with the maximum and minimum salary in their department, without collapsing rows like a traditional group by. For example, in the sales department, max salary returns $6,000 for every employee, and min salary returns $5,000. This is useful for calculating salary gaps, percentile analysis, or spotting outliers, all while keeping the full employee level detail. In the results, every row shows the same max and min values for their department. In sales, all employees see $6,000 as max and $5,000 as min. This allows direct comparison. Bob and Charlie are at the department maximum, while Alice is at the minimum. The key insight is that max and min window functions repeat the same value across all rows in the partition. This enables powerful comparative calculations like salary gaps, percentages of maximum, or identifying top and bottom performers.
Before we wrap up, let's understand why these functions are so powerful. Unlike regular SQL that processes data as it's fetched, window functions perform in-memory operations after your base data is retrieved, hence called online analytical functions. This means the database processes your rankings, running totals and comparisons directly where the data lives, no expensive data movement or temporary tables needed. It's like having a supercomputer inside your database that works on the final dataset. Frame clauses are the secret engine behind window functions. They let you define exactly which rows are included in calculations using keywords like rouse between for physical offsets or range between for value-based windows. This is how you create moving averages, cumulative sums within groups, or even complex time-based aggregations, all processed in memory after your data is retrieved. While we didn't cover frames in depth today, know that they unlock the true analytical superpowers of window functions.
We've covered how window functions unlock in-memory analytics power, processing data after retrieval for blistering efficiency. You can now rank, analyze trends, and calculate running totals in single queries. While advanced frame clauses like rouse between await our next tutorial, you're equipped with core skills that solve 90% of real-world scenarios. Thank you for learning with me today. If this added value to your SQL toolkit, please give the video a thumbs up, it helps immensely. Subscribe for the frame clauses deep dive coming soon. Until then, keep querying, keep exploring, and remember, every complex analysis begins with a simple over clause. Happy learning!